So what I'd like to do is round out the introductory material with this discussion on a brief history of C++. As you can imagine, C++ has been around for quite a long time, and so it's probably no surprise that many things have happened. I'm going to give you the abbreviated version of the history of C++, focusing on a couple of key things that happened along the way. And so C++ was designed back in the late 70s, very, very early 80s, by a researcher at what was then AT&T Bell Labs. His name is Bjarne Stroustrup. I will not attempt to pronounce his name correctly. I've known him for many years. He's a really good guy. And he always says that if you stick a potato in your mouth, it's much easier to pronounce his name, which is pretty funny. He also said when he goes back to his home country, which is Denmark, they ask him at the check, when you go through security, at the immigration part, they ask him who he is, and when he pronounces his name, they usually just let him into the country without even bothering to check his passport, because only people from Denmark can pronounce the name correctly. So C++ has been around for about 40 years or so. As the little sign here says, we're celebrating the 19th anniversary of our 21st birthday. That's kind of the way I feel about C++. It's hard to believe it's been around this long. And you can go to the link at the bottom of the page if you want to kind of get some artifacts that show the history of C++. It's really quite fascinating how this has evolved over time. And this was the original version of the book that he wrote. That was the first edition of his famous C++ programming language book. And I think it came out in 1985 timeframe or so. So if you take a look, here's a timeline that Bjarne created that kind of shows his view of how C++ evolved. And I wouldn't be surprised if he's correct, since he was the one who did most of it, at least in the beginning. And basically, C++ originated from the confluence of two areas. Number one were systems programming languages, most notably the C language, and also object-oriented programming in the vein of what was called Simula. And Simula has actually been around for a really long time. I think the original Simula release came out perhaps in 1967. So some of the concepts of inheritance and dynamic binding and so on from C++ were influenced by Simula. So you can see we kind of had the direct mapping to hardware style approach, which came from assembler and C and something called BCPL. And then the object-oriented parts of C++, at least initially, came from Simula. And of course, from there, a whole bunch of other things have spawned off. So if C++ got its start in the early 80s, then a little over a decade later, Java came around in the mid to early 90s. C# came around roughly the same time. And then, of course, all those languages have gone on to evolve in their own way, in their own pace. And C++ has also gone on to evolve in its own way and its own pace. Moreover, we'll talk later, C and C++ had a lot in common in the beginning, in the sense that C++ borrowed very heavily from parts of C. And of course, C has also evolved. But very few people these days use C as C. They usually use C in the context of a C++ compiler, just focusing on the C parts. It's getting very hard just to get a C compiler by itself, because the real market for this stuff is C++. The original version of C++, the original implementation, was something called C-front. And the reason it was called C-front was it was a front end to C. And so what it did, it was actually something called a translator, and it read what was in those days the early versions of C++ syntax, and then generated out C code. And there's some really interesting stuff. We're going to look at, for just kicks, at a snippet of C++ to C code from C-front. There are very, very, very few compilers that still do it this way. There are a few, but very few. And you'll see why in a second. It was not, this is not really the right way to go in a lot of ways. But that was the way it was done originally, because it made it easy to basically bootstrap C++, because there were lots of C compilers out there. And as long as they generated portable C code, then it was pretty easy to port to lots of platforms. So just for kicks, here's a little snippet of some C++ code on the left-hand side. And you can see this is a class called base, and it's got private, protected, and public data members, which are given very unimaginative names like private data, protected data, and public data. And then I also define a constructor, and the constructor is going to go ahead and initialize the private data, the protected data, and the public data. So you could have written code along these lines, circa 1980 or so. And what would happen when you ran this through Cfront is you would get the code that's generated on the right-hand side, plus some other stuff we're about to look at. So what would come out of this class would be a struct, because of course that's the primary data abstraction mechanism in C. And as you can see here, the fields are more or less one-to-one. The data members are more or less one-to-one, just with a little bit of syntactic sugar added at the end to say that they're part of the base class. That's just an encoding rule. And then there's also this other fourth field or fourth data member added that's called __v pointer __ for base. And you can see it's a struct __ m pointer. And this is the famous v pointer that would point to the famous v table. And we'll talk a bit more about v pointers and v tables later when we get into the object-oriented parts of C++. Right now, you don't have to think too much about this, but we'll cover it in just a bit. Here's what the constructor looked like. So on the left-hand side of this slide, I show you the C++ constructor syntax. And here's what was actually generated by the compiler at the time. So you can see that there's an __CT prefix here, which stands for constructor, of course. And then it's got some other gobbledygook with __ for base fi, and then there's this __ 0 this pointer and __ 0 arg pointer. The 0 arg pointer corresponds, of course, to what's passed in over here, and this pointer is a magic pointer that's generated by the C++ translator, Cfront, and that is the object that's being initialized or being created. And you can see down here that it'll do a bunch of stuff, and it might allocate the object dynamically, depending on various characteristics. And so what it's going to do is it's going to go ahead, once it's got it initialized, is it's going to go ahead and create the mappings between the various parameters that were passed in over here in the base member initialization section, which we'll talk more about in a second. And then we're initializing these things. And then you can also see that it's setting the v pointer to point to the appropriate location for the v table, which was an automatically generated array, basically, that kept track of the virtual member functions that were part of the class. And then at the very end, you can see it returns this pointer, and so it actually returns something. The constructor returns a value. Now, I think it's pretty clear that most people don't want to have to know how this works, myself included. And so this was all stuff that was done underneath the hood for you by the compiler. Now, the reason why they did this originally, as I mentioned before, was to bootstrap C++ from its humble origins into something that would run on C compilers, which were very common in those days. However, I think it's fair to say that if you were trying to debug your code in a debugger, which of course in those days would have been a C debugger, and you had to know all these crazy mappings, it was really complicated. And it also turned out that for more advanced features in the language, particularly exception handling, doing a C++ to C transformation or translation really wasn't the way to go because it was incredibly inefficient. And so as a result, people have moved away from C translation into native compilation. And there's lots and lots of C++ compilers today. If you look at the link at the bottom of this page, you can see that Bjarne Stroustrup himself has come up with a partial list because they keep changing. But some of the ones that are very popular, of course, are GNU C++ and the LLVM Clang compiler, which is what we're using for this course, most likely. You can use G++, but I recommend you stick with Clang and follow the instructions that are in the website because you're less likely to have headaches and be inconsistent with what I'm using. There's also compilers from IBM, obviously Visual C++ from Microsoft. Oracle, previously known as Sun, has something called the Developer Studio. There was a company called Borland, which I think is now called something like Embarcadero or something, that has a C++ builder. There's one from Intel. The list goes on and on and on, and you can follow the link here to see what they're doing. And the key point of all this stuff is that nowadays there's much, much better support. There's native debugging support, which is great. There's all these IDEs like CLion or Visual Studio that you can use in order to be able to develop native C++ code, which is very good. And I should also mention that C++ compilers have gotten incredibly advanced to handle the newer features in the language as well. So here's a very brief history of the evolution of C++. So you can see it started in 1979 when Bjarne, when he was at AT&T Bell Labs research, implemented this thing called C with classes. And the name C++ actually, I think, came out in the 84, maybe it was 83 time frame, something like that. The commercial release of the C front was given around that time. I started in 1986 to play around with C++. C++ 2.0 came out, which was a big deal. They began to standardize it toward the end of the late 90s. C++ 3.0 came out, and that had a whole bunch of improvements and was standardized. They had much better support for templates and so on. And then in the 2000 time frame, they started putting out this new version, which eventually became C++ 11. And that was a major improvement, especially in the form of templates. Much, much better support for generic programming and so on. The concept of C++ STL had started kind of in the early to mid 90s. I remember when it first came out and people's minds were blown for reasons we'll talk about later. But the compilers at the time really struggled with templates, especially the ones based on C front. And it wasn't until the 2000 timeframe, and especially the C++ 11 timeframe, when compilers really got good at handling the generic programming features that had been standardized. And then since that point, there's been three more releases: C++ 14, which added a few things; C++ 17, which added a whole bunch more stuff, including things like parallel STL containers. And C++ continues to be developed and evolved to this day. And you can take a look at the link at the bottom of the page to find out even more information about the history of C++. So the key points here are that it's been around for about 4 decades, and it continues to evolve, and it's way better supported by compilers and other tools than it was back in the early days. Certainly when I started out, it was only for people who really loved to play around with cutting edge, bleeding edge technology. Okay, so that's just a quick overview of this topic. Let's see, I don't think there's any questions at this point, so that's fine. What we're going to do now, as you'll see in a second, is we're going to turn our attention to the next topic, which is going to be looking at lots and lots and lots of examples. So heretofore, we've primarily focused on concepts just to give you a background and a basis for your understanding of C++. But from this point onwards, we're going to be focusing on lots of examples, and I'm going to show you with by example, which is the trademark of this course, how everything works, and you'll learn those things. So let's go back to sharing our screen.